Thank you very much. Good morning. So today I'll be presenting, good morning. My name is Abner Mendoza from the Success Lab at Texas A&M University. And presenting my work, mobile API reconnaissance, web-to-mobile inconsistencies, and vulnerabilities. This is a slightly different perspective of the mobile web integration problems that we just saw in the previous talk. So as we all know, there's an app for everything, right? There's an app that apps serve diverse functionality in society. And what is common in most apps is that they rely on this HTTP-based API services. And so if we take a look at the threat model or what the attacker capabilities are or the perspective of the attacker on this integration, we can consider in our threat model our attacker tries to, his goal is to compromise the web server, right? But obviously, it might not be feasible because the web server might have robust defenses. The attacker might also try to maybe intercept communication between the app and the web server, but there again, HTTPS, authentication tokens, and other things might prevent him from doing that. But just like any other regular user, an attacker has access to the apps. He can use the apps. He can be a legitimate user. And just like a security researcher, he can disassemble the app and analyze its inner workings, right? And so that might give him some insight into how to ultimately attack the web server. So if we take a step back and look at the evolution of web versus mobile application, and specifically from the perspective of where the business logic is implemented. On the left here, we have the typical architecture of a web application where the business logic and the heavy lifting is actually implemented in the web server, right? And the browser merely serves as for rendering the UI, let's say. And there might be a database layer at the bottom. If we look at the mobile application architecture, most of the business logic might be implemented in the app. These are compiled apps. And so most of the business logic, the validation logic specifically, might be implemented in the app, less so on the server, and the API. It might interact with an API server, which is also a web server, which in turn might interact with a database layer. And in fact, this web and API server that I show here are one and the same, right? So on this work, we focus on the difference between the logic that's implemented on the application layer, on the mobile app specifically, and then what's implemented on the server. And of course, we expect some consistency there. So the problem that we try to highlight here in this work is that server-side input validation is still important, although that business logic has shifted. And inevitably, with this integration of mobile and web, inconsistencies will appear. And as I said, attackers can discover and leverage these validation inconsistencies to compromise the server side. So our attack model, again, I want to emphasize that the attacker does not attack the apps. He does not deploy a malicious app. He merely analyzes the apps. So in this example, in this simple example here, we have our bank application communicating with, let's say, it's bank.com server, right? And so in the implementation of this app, let's say a user wants to do a transfer of money from Alex to Bob. The application might send a web request with some certain parameters that define the amount and who the money is coming from and who's it being sent to, right? This is all validated by the application and also validated by the server, and the transfer happens. So the attacker can analyze the application to uncover this particular API endpoint, among others, and the different parameters and the data types of those parameters. And the attacker might try something, right? It might not be successful, but at least he has some knowledge of where to send a web request. The server, if it's implemented properly, will reject that. But if it's not implemented properly, the server will accept that invalid from the perspective of the app input. Right? So he might change where he's sending the money to and send it to himself from Alice's account. So in our research, we do a systematic approach for detecting these types of mobile to web validation inconsistencies. We implement a system what we call Wardroid, which is a web API communication reconnaissance framework for mobile applications, specifically implemented in Android. And then we highlight some real-world case studies of vulnerable apps with some fairly severe impact. Our general approach to this is first we analyze the apps to uncover that logic, just as an attacker would do. We use the observed constraints that we uncover from analyzing the app to build these, what we call these communication templates, or HTTP request templates, that the app uses to communicate with the API server. And then we evaluate variations of this template with some intentional invalid input. And if the server accepts the input, then we kind of flag that app and do some more manual investigation. So let me walk you real quick through the overall architecture of our system, Wardroid. So it starts, it takes as input the Android APKs, and it feeds that into a static analysis module. Right? In our static analysis module, among other things, we primarily have this HTTP-aware program slices, which kind of reduces the search space for analyzing the app to just those methods and its dependencies that initiate HTTP communication. We additionally augment that dependency graph with some UI element analysis to kind of get more idea of what the data types are and some other constraints on those input data. And so this gives us a set of path constraints, right? And using those path constraints, then we can build these HTTP templates, which are guides to how valid inputs or valid requests to the API server might be constructed by the app. And then we feed this into, use these templates in our evaluation module that basically takes these templates, generates some requests, both valid and potentially invalid from the perspective of the constraints that we observed in the app, valid and invalid requests. And then we do some testing on the responses, right? So we're testing the server in a black box fashion to try to determine whether whatever request we sent with parameters that might be invalid, whether the server accepted it or not. And so then the output of this is just the reports of the different apps and what looks like potential vulnerable API endpoints. Then we can go in and manually verify and test these to validate them. So just to kind of give you a better idea of maybe how these are extracted, these templates are extracted. This is a simple implementation of what in Java HTTP request how it might be implemented. Here in line 6, the application is sending out a URL connection, a request, and then so this is our point of interest, and if we analyze it backwards from here, we can perhaps get all the dependencies, all the input, all the parameters that are being sent in this request. And so we start out for our point of interest and we go backwards, right? We go and we identify the connection setup, and this will give us, among other things, this is just a simple example, but among other things, we get the method, which might be a HTTP GET method. The scheme might be HTTPS. We identify the API endpoint, and it might tell us the domain, bank.com, and the path, which is to the transfer functionality. And then we identify the particular URI parameters might be included in this. And you might say, well, we have the from, the to, and the amount. And then we augment that with analyzing the user interface. And it tells us some additional constraints on those parameters. So in this case, maybe it says from the Android manifest file, it might tell us that the type is text, the maximum length is 100 for the text fields, maybe the amount field is a double type, just as an example. And so putting all this information together, then we can see how we can generate a valid request, right? And of course, leaving out a lot of details from this, like the HTTP headers and the content section of the HTTP packet. So our request templates are modeled after the HTTP protocol fields. So it extracts method, scheme, what the URI might look like, what the body and the content, and includes all the constraints in those, right? Particularly the last 3 fields. And so those are what we use to kind of, this tells us what a valid request is, and then we can figure out how to manipulate those to do something perhaps malicious. So lastly, then our evaluation or inconsistency evaluation module then takes these templates and it generates both valid and invalid requests. It generates valid requests to kind of determine a baseline of what a successful response from the server might look like. And so then it determines success versus failure based on some testing or evaluation and a particular pattern matching of those response strings. And so then if an invalid request is successful, then a potential vulnerability is found. And so we say potential because then it requires some manual validation of actual, that the vulnerability actually exists. And some human intelligence is required there. So I'll quickly highlight some of the case studies that we found. First, our tests consisted of 10,000 apps. We did a large-scale evaluation, 10,000 apps. We were able to generate over 16,000 invalid requests, multiple for the same app. Our system identified or flagged over 4,500 apps with potential issues. And then we tested manually 1,000 of these apps and verified that 962 of them had some API validation logic problem with varying degrees of severity, right? The estimated, based on those apps that we validated, we estimate that the victim population could be over 6 million, just based on the estimated download counts on the Google Play Store. Again, the degree of severity varies, right? So one case study in a major bank application here that does, or in specifically the money transfer functionality of the application. Again, I want to again step back and say these have all been fixed in these applications. In all instances, we notified the developers, and some responded, some did not. So in the bank application, specifically in the TOOF, the field where we select the account that we're sending money to, of course, there's an implicit constraint that enforced by the app that you can only select what is available in that spinner. And so using our multiple test accounts in the app, this is back in the day when you could get a free account without the banking fee. And so we had multiple accounts set up and we were able to transfer some money even though the account number did not appear in our app or authenticated, validated in one particular account. Of course, there's authentication constraints here, which is kind of a limitation of our work. Another case study is our gift card app. And in this particular app, there was a problem. Actually, we uncovered really a SQL injection problem in the login interface, and just how the app or the server side did not properly validate the input being sent from these login fields, particularly the password field. And so then we were able to, using our own test accounts, again, just transfer values from the gift cards from one account to the other. We were able to, we actually notified the app developers, and we worked with them to uncover some more serious issues where it turns out all their user accounts were exposed, and we were able to help them fix this problem. And the last one I want to highlight here is the apps that use the Shopify SDK. And so we set up our own Shopify merchant store with some demo products in there, and then we use their SDK to build a test app, and found that in the add to cart functionality in the API, you have to send information on your product, including the price. The app or the SDK itself validates the price, so you can't send a negative price to the SDK. Right? So that constraint informed us that, okay, if the app is validating that you can't do a negative value, maybe let's check if the API server does. And so by bypassing the SDK, sending the add to cart functionality or replaying that, but with a negative number, we're able to successfully add to our cart a negative amount. And this is because, of course, the need for the flexibility, for example, to accommodate for coupons, maybe we're at discounts. And so the price might vary from one user to the other. And so we notify these. This is, again, has been fixed on the server side. From all these, so some of the recommendations that we kind of, based on our insights, of course, you never want to trust the client input. And of course, this is a harsh lesson that should have already been learned from our lessons on the web platform and web applications. But this work highlights that this continues to be a problem, input validation, and just being very cognizant of validating or sanitizing input. So server input validation must be at least as strict as the client, but not less strict than the client, and that seems to be the fundamental problem. We also saw in some of the cases we looked at confusion between authentication and authorization logic. Whereas, as long as you're authenticated, authorization is not checked on the server side. And that, again, a harsh lesson that should have been learned from the web platform, but continues to be a problem. So the key message here is that consistency is key between the server and the client validation logic, and unfortunately, doesn't seem to be the case. So in conclusion, we show that input validation remains a problem on this web mobile to web API services and this integration of mobile and web. We developed a system Wardroid, which is a system that can be used to uncover these types of validation inconsistencies in a semi-automatic way. And we highlight some case studies, and our evaluations show that inconsistencies in validation logic, particularly server-side validation logic, remains a pressing problem. So with that, I want to thank you for your time, and we'll be happy to welcome some questions.
Hi, Nick Nikiforaki, Stony Brook. Can you tell us a little bit more about the authentication step? Because you seem to be statically extracting URLs, and one would assume that you need some sort of token that would be dynamically exchanged between the app and the server.
Right. So that is one of the, actually, we talk about it more in the paper, but it's actually one of the limitations of our work. And that is why, that is one of the primary reasons the manual step is required, where after it has been flagged as something might be potentially vulnerable, then we have to authenticate with our own account, our own demo accounts, and trying to manipulate parameters that way. So
how would you know that something is potentially vulnerable if you cannot send the first regular request with the right token?
Because so the application, based on the logic in the application, we can uncover the template, right, the guide on what a request might look like. And it might show us that, okay, there might be an authentication token required here. So one of the fields is an authentication token. Obviously, we won't be able to automatically generate that. And so then we have to step in and get that some other way to be able to replay that.
I see.
Yeah.
Okay, thank you.
Very well.
One more question? Yeah, hi, Phoebe Rouge, the Federal Trade Commission. Thank you for this work. I thought it was really insightful to look at this particular issue. Do you think that this is also, you looked at HTTP and web server API requests, do you think this might be a problem too with like Android deep links and things that connect apps in between too, those types of requests?
We didn't specifically, well, it potentially could be. I am not sure, and we certainly didn't look at the issue with deep links, so I wouldn't, I'm not sure I have
Thank you.
much insight into that.
All right, let's thank Abner one more time.